Last class, we considered a adaptive filter, though we did not use LMS or any mode of adaptation, just an adaptive filter where filter coefficients are varying with time, and at nth index, nth clock, filter coefficient vector is Wn, and we had Vn was the error between the actual filter coefficient vector at nth index minus the optimal one. Okay. And then if Wn is used, just for recalling, if Wn is used as a filter, so filter output was W transpose, filter output was and corresponding error was En, Dn minus this. This is Yn. Since I am not using W opt here, this error will have variance power higher than that of the case when I use W opt, Dn minus W opt n xn. Okay. And that error is called E opt n, where Dn remains as it is. This is all from previous day's lecture, a quick recap. Okay. So, variance of this is larger than the variance of this, because this is where I use the optimal filter, and the difference between them we are trying to work out. And what we found is this, that is, if you denote the variance of this noise, this error, as the minimum possible variance, so epsilon square mean, and here if you say as just epsilon square n, then epsilon square n under some independence, generalized independence assumption, which I did last time. This is having this component plus an additional component. Sorry. R is positive definite, and therefore, any Vhn, as long as Vn is not 0, okay, in an average. So, this will be for any Vn. Actually, Vhn I am writing, I could as well write transpose, because they are all real. I am considering only a real case. So, any V transpose n or Vn will be non-negative, and if Vn is positive, it will be positive. Since Wn is different from W opt, Vn will be in general non-zero, maybe in one particular trial could be 0, but in general non-zero. So, when you average, you get a positive term. Okay, this is that extra component. This is called excess mean square error, epsilon square excess at n, excess mean square error. Okay, so let us work on it. We know that R is a positive definite matrix, means R is a Hermitian matrix. We had studied at length in the beginning of this course some properties of Hermitian matrices and positive definite matrices. We know in these cases the eigenvectors of R corresponding to different eigenvalues, they are all mutually orthonormal, that is, each having norm 1 and they are orthogonal. And if I put them side by side, this matrix is T. R can be written as T, then a diagonal matrix D, where D consists of diagonal entries only, and those are the eigenvalues, and eigenvalues are positive, not only real, positive, because it is a positive definite matrix. Okay. And the same TH, T unitary, because all the columns of the T are mutually orthonormal rather, meaning we have all studied this, so no question of going back there again. THT is identity, which is also, that means one is the inverse of the other, therefore, you can put T in the beginning and TH here, that also is identity. Okay, this is what we studied earlier. All right. Let us consider this expected value of V transpose n or Vn. I will replace R by this after a while. But before that, let us see one thing. This is a scalar. Okay, row vector, matrix, column vector. Matrix into column is a column vector, row into column is a scalar, right? Of course, because left hand side is a scalar. expected value of that. So, scalar is a 1 by 1 matrix. So, trace, we know the term trace. Trace of a square matrix is a summation of the diagonal entries. So, a scalar is a 1 by 1, that is square matrix. So, its trace will be that element itself, isn't it? So, this scalar I can write it as a trace, this term excess term I can write as trace of this quantity scalar term. All right. Because this thing, whole thing is a scalar. Scalar is a 1 by 1 matrix which is square, and therefore, trace of that is that element itself. So, this whole element is nothing but its trace. Now, there is a result that if A suppose is a M cross N matrix and B N cross M, then trace of AB, and AB is a M cross M matrix, the trace of that square matrix is same as trace of BA, which is a N cross N cross matrix. I am not sure whether you know it or not, but it is very easy to derive, which I do for your sake. So, trace of, from here we see trace of AB, AB if I call a matrix C and BA if I call a matrix D. Trace of C means all the diagonal elements are to be added. So, C I comma I is a ith diagonal entry. So, I start at I equal to 1 to how many? It is a M by M matrix, right? M cross N cross M. So, it is at M by M and this is a N cross N. So, I equal to 1 to M. Now, what is CII? AB you are doing product, right? So, ith row of A, ith column of B, when you are multiplying you are getting CII. So, that means A ith row, and you span the rows by using a index j, and j can be 1, 2, how many A up to n. So, A1 I have not completed yet, but I span like this, scan like this, I1, I2, I3, like I1, I2, I3, I4 like that. So, I am going along the row and simultaneously I am moving B in this direction J I. So, ith column. So, B 1 I, 2 I, 3 I like that. So, B A I 1, B 1 I, A I 2, B 2 I, A I 3, B 3 I like that. So, ith row and j ith column, ith row and ith column of ith row of A, ith column of B, they are multiplied, that gives me the I comma I diagonal entry of C. So, this is my CII, and then whole thing is sum because it is trace, I am taking trace over this. Now, you know any double summation means what? First you fix a value of I, for that I you move j over the entire range, carry out the summation. Then again take another I, fix that I here, and then move j over the entire range, carry out the summation, and do on doing it and then add all of them. I can do the same thing if I hold j first at 1, take all values of I, then again another value of j, take all values of I, okay, and so on. In the end I will get the same result. Okay, this is called interchanging the two summation or summation order. So, first you fixed j equal to 1 to n, then you for each j you move I equal to 1 to m, aij bji, I write this way, bji aij. What is the meaning? Jth row, ith column. So, j1, j2, j3 as I moves, and here jth column as I moves 1j, 2j, 3j like that. So, it is the jth row of B and jth column of A, they are multiplied, which will give me the j comma jth diagonal entry of this product matrix. All right. So, it will be D j comma j. all right. So, it is nothing but B A if you do, and you find out the jth diagonal entry, then jth row of B. So, here j is fixed, I moving, j1, j2, j3, and jth column of A. So, here j fixed and I moving, they are multiplied and summed. So, that gives you the j comma jth element of D, jth diagonal entry, and then you are summing. So, you are taking a trace of this product, trace of B A. This proves trace of A B same as trace of B A. Therefore, if you consider this down, you take this to be row into matrix is a row, that is also a matrix after all, m cross 1. Okay. You call this to be like your A, and this you take to be B. The trace of A B, because A and B are not squared, they are arbitrary, m cross n, n cross B. So, m can be something and n can be 1 like here. So, it is a row vector and so on here. So, trace of A B will be same as trace of B A. So, trace of V n, V transpose n R. So, we will have trace of E outside, trace of we had, let me remember, V transpose R V, and this V will come in the front. R. Now, you see this is a matrix, V n is a column vector, V transpose is a row vector. So, this is a matrix, this is a matrix, this is a matrix, together is a matrix, but square matrix. R is square, V n V transpose is square, square into square is square. So, trace of square matrix, then expected value. That means, whatever is the matrix, I take the summation of the diagonal entries, then apply E over them. I will get the same thing if I apply E over all the entries of this matrix, product matrix, and then take summation of the diagonal entries only, isn't it? Here you first take the sum of the diagonal entries, then apply E on the diagonal entries. But you can do this, get the same thing if you apply E on all the entries of this total matrix and then take summation of the diagonal ones. You will get the same thing. So, that is called interchanging the two operations. So, trace E goes in, E V n V transpose n R, all right. But R is not random. So, this is a matrix where all the elements are random, because V n consists of, V n is what, W n minus W opt, and W n is random. So, V n is random. So, this is a matrix where every element is random. That matrix should be a constant matrix. If you carry out the product and then apply E, you will get the same thing if you apply E on every element of this matrix and then carry out the product. This we have done earlier. So, it will be nothing but trace of E working on this part or outside, all right. What is V n? V n transpose E is the autocorrelation matrix of V n. So, let me call this K n matrix. Remember, it is not stationary in general, and therefore, I am putting an index n, unlike R. It was the input autocorrelation matrix independent of n, because input was WSS. Same does not apply here for Wn, where Wn is not in general WSS. Okay. So, I call it Kn. Kn is E is called weight error vector. So, weight error, Vn is weight error vector, weight error correlation matrix. You can say autocorrelation or simply correlation, weight error correlation matrix. All right. So, this I take to the next stage, next page. This is the excess term. trace of Kn R. And now I replace R by what I told earlier, T D T H. And again take this to be one matrix and this is another matrix A B. So, trace A B is same as trace B A. So, it will be trace of right. This is the thing. This I give a new name K prime n, which is transformed weight error correlation matrix. I will explain why you call it like this. I know K n we have seen already, it is E of V n V transpose n. Okay. Now, this T is a Hermitian, T is a unitary matrix. Suppose I define V prime n as T working on V n. So, it is transformed. T is a transform, it works on V n, gives you V prime n. So, it is called transformed weight error vector. So, autocorrelation matrix of these V prime n, V prime transpose n will be what? You replace it T V n here and T V n transpose, it will be V transpose n. So, V prime n, T V n and V transpose, T transpose. So, this is one matrix. T is not random, constant, T transpose not random. So, if we carry out this matrix times this matrix and then this and apply E on that, you will get the same thing if you apply, because that E will work only on the elements coming from here. You will get the same thing if you apply E on this matrix first and then do the product. Okay. This kind of things we have done many times. So, this should not be a point of confusion. So, it will be and this is my K n. So, this is T K n T transpose. Okay. Let me do one thing, instead of this V prime n, let me make it T transpose V n. So, it will be T transpose and this transpose will go. I am changing the definition. Okay. So, T transpose and this will go. So, this T transpose and this will go, which is my T H here, but we are dealing with real cases. So, T transpose K n T, T transpose K n T, which is K prime n. Okay. So, what does it mean? This K prime n, which was T transpose K n T, which I call K prime n and name this transform weight error correlation matrix. Actually, if I define a new weight error vector, transformed weight error vector, T transpose V n, T transpose is a transform matrix. Then if I take the autocorrelation matrix of V prime n, I get back this K prime n. So, that is why it is the autocorrelation matrix of the transformed weight vector, it is called transform weight error correlation matrix. All right. So, this if we take a look, we have trace k n r, which is given here. Okay. So, trace k prime n d, and I explained what is k prime n, I defined. So, then combine everything, total epsilon square n is epsilon square mean plus this extra term is this trace of one autocorrelation matrix times a diagonal matrix. Diagonal matrix consists of lambda 1, lambda 2 up to say lambda maybe capital N if there are n such entries. Okay. So, if you have a matrix, square matrix and multiply by a diagonal matrix, first column all the elements get multiplied by lambda 1, second column all the elements multiplied by lambda 2, third column all the elements of k prime n get multiplied by lambda 3, so on and so forth. You can verify. Then if you take the trace, it will be lambda 1 times 1 element plus lambda 2 times 2 element plus lambda 3 times 3 element and so on and so forth. So, it will be lambda I k prime I n, I can be, I do not know what range I took earlier, 0 to n minus 1 or 1 to n or maybe 0 to n minus 1. Okay. These are the diagonal entries. This is the extra term. Okay. This is called excess ABC, okay, epsilon square excess at n, all right. This is something that it is a superposition of capital N number of sequences. What sequence? This k prime IIN, this sequence. If each sequence does not grow with time, but decays or at least remains at a finite value, that is as ends to infinity, they have a finite limit, then the overall sum also will have a finite limit, and these are all non-negative because these are variances. In autocorrelation matrix, I am taking the diagonal terms, and lambdas also are positive because they are coming from capital R matrix, which is positive definite. So, these are actually positive sequences, positive valued sequences. If every sequence goes to a finite limit as n tends to infinity, that is in the steady state, then the summation also will lead to a finite limit. It will not grow, but if it grows and grows and grows, if any of the mode, if any of them, each is called a mode, 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 convergence mode. So, there are capital N convergence mode. Each mode is characterized or given by one particular k prime IIN sequence. Okay. So, if any of the modes now becomes unstable, grows to infinity, shoots up, then the same happens for the whole, and therefore, this error becomes unbounded, and that is a thing we want to avoid at any cost, because the error goes unbounded, then the algorithm fails, isn't it? So, therefore, we should make sure that these functions actually each of them converges to a finite limit as n tends to infinity. Okay, they converge to finite limit, and then we will try to see how much that limit is, on what does it depend, and how to make it small. Okay, that will do our purpose. Okay. So, that means what we will do is we will evaluate this. This should be for stability of the algorithm. Now, under stability, condition, suppose this is satisfied, under this, if so happens, then obviously this entire thing is finite. Okay. We just normalize it to epsilon square, this mean, epsilon square mean, okay, and give it a name. This term summation lambda I as it is I equal to 0 to n minus 1, just divide by, normalize to this. This is called misadjustment. Obviously, under stability condition, and we denote it by m, misadjustment, m should be finite. Okay. Now, this m can be worked out. This is a very lengthy procedure, though very educative procedure. One gets to learn a lot of techniques, tricks and all those, but then in this short course, I cannot go through the derivation. So, I will give you the formula of m that people derive, and that is m equal to 1 j by 1 minus j, where j is our summation mu lambda I. So, for each eigenvalue I equal to 0, I equal to 1 up to this. So, I have one term mu lambda I by 2 minus mu lambda I. So, mu lambda 0 by 2 minus mu lambda 0 plus mu lambda 1 by 2 minus mu lambda 1 dot 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 dot. Okay, this is j, and j by 1 minus j is m. Okay. Remember, m is what? After all, a positive number, because it is variance. Okay, excess means square error by minimum means square error. So, it is a variance, positive thing. Therefore, m we will consider only when it is positive and then analyze. Okay, its dependence on j and all that we will find out. Okay, when m will not shoot up to infinity, because if it is unstable, m will shoot up to infinity. All those things we will do in the next class. Thank you very much.